Okay, good morning, everyone. Thanks for all coming. We're very excited. So let's get ready for it. Our first speaker this morning is Linh Truong. And she'll be talking about four-ball genus bounds and the 10x plus 4 theorem.
Good morning, everyone. Thank you for the invitation to this workshop. It's my first time here at the University of Science. I'm really excited. So I'll be talking about joint work with Sashka, Kjuchukova, and Gordana Matic. Talks about four-ball genus bounds and the 10x plus 4 theorem. So I'll begin by calling what the definition of the four-ball genus of a knot is. If we have a knot K of 3, the four-ball genus is defined as the minimum genus of a contact-oriented surface smoothly embedded in G4, whose boundary is R. So R naught lives inside of F3, which is the boundary of the four ball. And for example, some knots with four ball genus equal to 0 are, if you take any knot and you take the reverse orientation of the mirror of the knot, this will be an example of a knot with four ball genus 0. This is what's called a splice knot. Splice knots are knots whose four ball genus vanishes. Other examples include the trefoil knot, which has four ball genus 1, and in general, four ball genus of P to the quarters knot is P minus 1, 2 minus 1 over 2. This is also equal to the unknotting number of the torus knot. This is what's called the Milnor conjecture, which was proven by Frankenheimer and Rosa using gauge theory. There are other methods of computing the four-ball genus of a torus knot using lower bounds on the four-ball genus. So, for example, an example of the lower bound of the four-ball genus comes from knot square homology. The tau invariant is the lower bound due to Alvarado, which is sharp on torus knots. So again, we use the Milnor conjecture. Another example of a lower bound is the S invariant from Gordana homology proven by Hopkins. Which is purely combinatorial proof of the Milnor conjecture. And as another example of a lower bound, more classical knot invariant is the knot signature, which is the signature of the cipher matrix plus the transpose. So these are some examples of four-ball genus and lower bounds on them. This talk will be talking about how to produce a four-ball genus bound on a knot using two handle body theory and some Kirby calculus and the 10 theorem and 10 theorem. So in the talk, when I say two handle bodies, I mean a four manifold that's a union of a four ball with some two handles attached. So these are four-dimensional two handles, so they're copies of U2 times V2 attached by embedding maps of S1 times V2 into the boundary of V4 or S3. So they're specified by two pieces of data, a knot living in S3 and framing on the knot, which tells the size when that's how. An example of a two-channel body that we'll be interested in is the knot frame. So in particular, the zero frame, genus, knot frame. So we try zero. Okay. So this is the four manifold that we can construct. Given a knot in S3, we can take a four ball. Union of four-dimensional two handle. So this is the case for zero. Handle attached along K with the framing zero. But so then this two handle attachment is when you're gluing on a V2 times V2. But for the higher genus analog of this knot tree, you can glue on a copy of surface times V2, where the surface is a compact oriented surface with one boundary component. This is higher genus handle attachment. We'll call this a irregular is E handle. And just like with a traditional handle attachment, this map or this handle attachment is determined by two pieces of data, a knot living inside of a boundary of V4 and a framing on the knot. So again, this is a surface of boundary. The boundary of the surface is a circle, which will identify with the knot. And the circle is long. Okay. We're identifying surface. This boundary is zero with the knot. So this is an example of a two-panel body. And we're interested in knot traces in the classical G equals zero knot trace setting, because, for example, there's the trace embedding lemma, which tells us that a knot trace embeds usually into S4 if only if the knot has four-ball genus zero. And there's a higher genus analog of the trace embedding lemma, which is for zero frame genus do not exist. They will usually embed into S4 if and only if the knot found surface of genus G in four-ball. So the four-ball genus should be less than 8. Before I write down the lemma, I'll also write down a curvy diagram describing this four manifold. So I'll take, a zero frame two handle attached to the knot K, and then we'll take 2G1 handle. There are G copies of these pairs of a knot. All of the linking numbers between the link components here are 0. Sorry, drawn correctly. And so there's a single 2 handle and 2G1 handle. This is the Kirby diagram describing this genus G knot trace. And we have our trace embedding lemma, which says that the four manifold given by this knot trace will smoothly embed into S4 if and only if the knot bounds a surface of genus G in the four ball. So in other words, the four ball genus should be less than or equal to G. Is it okay if you erase this? So our theorem uses this existence of an embedding of the knot trace into S4 if the four ball genus is equal to G, like hey, be a knot in S3 with four ball genus equal to G, then we know that S4 is the union of the knot trace with some complement V. We call the complementary manifold here V. And also suppose that S is a thin two-handle body with boundary of X diffeomorphic to the boundary of the knot trace, the genus G zero frame knot trace, such that you can form the closed smooth four manifold X union V, and you should have that closed manifold also be spin, so admit a spin structure. So under these conditions, if we look at B2 of X and the signature of X, we can find a relation on them as long as we're not in one of the exceptional cases. So as long as we don't have B2 and signature equal to 1 minus 2G common 0, 3 minus 2G common 0, or 23 minus 2G plus or minus 16. Then B2 of X is bigger than or equal to 10/8, absolute value of the signature, plus 5 minus 2G. So this theorem says if you start with a knot in F3, whose four-ball genus is some G, you can split S4 into these two manifolds, the knot trace and V. And if you can find some spin two-handle body, some four manifold whose boundary is the same as the knot trace, you can glue that onto V. And if you can show that that closed manifold is spin, then you have this relationship, this inequality between the B2 and the signature of the four manifold. So if you look at the G equals 0 case, then we're talking about a splice knot, and this was previously proven by Donald and Vafaee using the 10/8 theorem, and it can be improved to an inequality with the 10/8 plus 4 theorem. A key difference between this setting with G equals 0 and the higher genus case is that in the genus equals 0 case, you don't need this F union V being spin condition, because that will automatically be satisfied. If you can find any spin X, you can always glue it onto the manifold V, which is the complement of the genus 0 knot trace, and the spin structures on the boundary will be compatible in the genus 0 case, because there are two spin structures on V, and both of them will extend over any spin two-handle body that you're gluing in. So that's a key difference between the genus 0 case and this setting, is that we're including this assumption here because it's not automatically satisfied for every closed manifold that you get by gluing X to this V. Also in the genus 0 case, Donald and Vafaee show that this splicing obstruction can obstruct a knot from being spliced. Where being spliced means the four-ball genus is equal to 0. Empty chiral knots, so knots where they're isotopic to the mirror, and topologically spliced knots. So knots where the topological four-ball genus is equal to 0. Wait. So as an application of a four-ball genus bound that you can produce from the theorem, we can look at satellite knots with companion any knot K. And let's assume that K can be unknotted by P positive to negative proximal changes. So you can find a diagram, a knot diagram, where there are P numbers of proximal changes. You can do knot for knot, where we're assuming that each of the proximal changes begins with a positive crossing and ends with a negative crossing. Then our theorem the satellite knot with companion K and pattern, a twisted torus knot P of 2n 4kn plus 1 R F. So you should think of this as starting with the torus knot 2n 4kn plus 1 and taking F adjacent strands. So the torus knot here has 2n strands. You can draw a diagram for it with 2n strands. You can take F of those adjacent strands and do R full twist on them. So I'll draw here that. So this is our pattern knot, and you can use this and companion K with this condition on the number of crossing changes to unknot it. Then the satellite knot has 4-ball genus bounded below by K n squared over 2 plus R s squared over 16 minus 916 R. Plus we have minus 3 halves NP minus 1 half P plus 1 half N, where we have here some assumptions on N, K, R, and S. Want these numbers to be positive and F and R, and K also positive and less than NP plus P. So with these conditions on the boundary, we can write down this as an example of a 4-ball genus bound that you can get from this theorem using 2 handlebars. Are there any questions so far?
I'm still trying to understand this in another theory. So like most of it doesn't depend on B, right? So like it looks like it's, so you have, if you have a 4-manifold, spin 4-manifold, the 2 handle bodies, so that the induced spin structure on the boundary is something, but the boundary is one of these generalized surgery, right? Like you do instead of the usual 0 surgery, you're going S1 times.
Yeah.
Outcome. And like one, so the point of writing it that way is that the induced structure on the boundary is something fixed, right?
Right. So the point of writing it like this is that if there's a spin structure on X that will restrict the spin structure on the boundary of X, that spin structure has to be able to be extended to a spin structure over V. And there's only 2 spin structures on the boundary that will do that. But the boundary has many more spin structures. For the entire genus cases, the boundary has 2G plus 1 spin structures.
The boundaries of S1 times sigma G models, right? You get one question, which is spin structure on S1 times sigma G is X1 times sigma G.
Right, so that's something I'll be talking about in a bit. Yeah, so when we're applying this theorem, so first I'll give a sketch of this theorem, and then I'll talk about the general framework for how to apply the theorem, how to show how do you guarantee this condition that X union B is fixed.
The inequality you wrote ever equality.
So we haven't found any examples of knots where this inequality is sharp. But at least I think it's on the right order of magnitude. If you plug in some numbers to check, for example, just checking with R equals 0, the pattern is a torus knot, and then you know what the four-ball genus is, and you would get at least the right order of magnitude for that with the kn squared term here. And then okay. So it's not sharp even for torus knots, but it's the right order of magnitude.
Do you compute tau or this guy?
Yeah, that's a great question. I didn't compute tau for these guys. I know you can compute tau of cable knots. There's a paper by Ben that does that. But for these patterns where you have a torus knot with some extra full twists where the full twists aren't taking all 2 strands, but a subset of them, I don't know how to compute tau in general for this. So I think that's one thing that our method can handle pretty well, is that if you take these extra full twists, working with our method, we can compute them down. Yeah. Yes. Yeah. Right. So I think I didn't write down the other inequalities where you vary the parameters and allow for, say, R is negative and see what you get, but you can do that, and our method would also it would be the same method for how to compute the bound, and then you would break out the new bound for that. So the proof of the main theorem, actually before I do that, were there any other questions?
Yeah, like why is excluding those?
Oh, why am I excluding those? So the inequality is coming from the 10H plus 4 theorem, which gives a lower bound on B2 and signature, or there's this inequality relating B2 and signature of opposed spins to 4 manifold, but they exclude S4, S2 times S2, and B3. So those are where those numbers are. Anything else? Great, so I'll just go over the proof of the main theorem, which is analogous to the Gables 0 case, which was proven by Donald and Vafaee. So recall, S4 is the union of this knot tree together with B. And we have our spin 2 handle body X, which has boundaries isomorphic to the knot tree. Let's call W the new manifold X union B. This will be closed to, and by assumption, then by again and then argument, you can show that I1 of W 0, so it's disconnected, and we have B1 damages and B3 damages by gray cloud. And then since X is a two-handle body. And also two numbers. So B1, B3, B4. Zero. And we want to relate the B2 and signature of W to B2 and signature of X, so that we can apply kind of +4 to W and get an inequality relating those numbers for X. So let's use the Euler characteristic, which is additive. So for W is equal to Euler characteristic of X B, and then writing out numbers, plugging in these numbers, you would get B2 of W is equal to B2 of X plus 2G minus 1. This is using the fact that the Euler characteristic of B is equal to 2G, which you can see by computing the homology of B using, for example, Alexander duality, because you know we get the complement of that genus G not traced in S4, and we know exactly everything about this genus G not traced. So great, we have this relationship between B2 of X and W. We also want to relate the signatures of X and W. The signature is additive. But I know we have additivity. We have signature of W is equal to signature of X plus signature of B. But we also know that signature of S4 is equal to signature of the not traced plus signature of G. And these vanish, so signature of B is equal to 0. And so signature of W is equal to signature of X. So we've related numbers, B2 and signatures of W and X, and then we want to just go 10 plus 4 theorem. Due to Hopkins and Kjuchukova, which improves on Furuta. So their theorem says that we have this closed smooth spin 4 manifold that's not S4 or S2 times S2 or S3, then you have this relationship B2 of W bigger than or equal to 10 signature of W plus 4. As long as your W was not one of the 3 manifolds, so then you'll just plug in our numbers for X into the inequality, and we'll get B2 of X bigger than or equal to 10 signature of X plus 5 minus 2. Was there what we wanted? So maybe I will leave the main theorem up here for now. talk next about how we're able to apply the theorem, which involves checking whether a spin two-handled body glued to this V is spin. So we'll go over how we'll represent the spin structure on the boundary of X. Boundary of X is a closed oriented three manifold. So spin structures will be in one-to-one correspondence with what are called characteristic sublinks of the length diagram, specifying the Kirby diagram for X. So X is a two-handled body. Its Kirby diagram can be given by a framed length L in S3, which tells us how to attach all of the two handles or all of those copies of D2 times D2 into the boundary of the D4. Then spin structures on the boundary of X are in one-to-one correspondence with characteristic sublinks of L. And I'll go over what that means. And if you take a spin structure that extends over X, if you take a spin structure on the boundary which extends over that two-handled body X, that corresponds to the empty characteristic sublink. So your length has M components. A characteristic sublink L prime of L is a sublink such that the linking number of Li with Li, which is just other notation for the framing of Li. This should be congruent mod 2 to the linking number between Li and L prime. Again, spin structures, if you apply this framework to the knot case, spin structures on the boundary of the knot case are in one correspondence with characteristic sublinks of this knot case. Where here, so this is a Kirby diagram for two handle bottoms where I've taken my unity knot case and I've replaced all of the one handles with zero frame two handles. this is a different form manifold than the knot case, but its boundary is the same.
It's funny.
But characteristic sublinks of this diagram, where this is the link L, specifying a content quantity, whose boundary is the same as the boundary of the knot case. They're just the same as sublinks of this link, because all of the linking numbers and equations are 0. So So we're interested in spin structures on the boundary of the knot case or the boundary of this diagram that will extend over the manifold of V. And so the next proposition here is exactly about that. Suppose S4 is decomposed into these two pieces, the knot case and V, then there are two spin structures on the boundary of V, which extends over the horizontal V, and they are distinguished by whether K lies in the characteristic subgroup. So boundary of V is the pleomorphic to the boundary characterization of this surface. So the spin structures on the boundary of V are again in one-to-one correspondence with sublinks of this diagram. And there are exactly two sublinks that will give you a spin structure extending to V, and one of them doesn't contain the knot K, and the other one does contain K, but possibly with some other links.
So just so I make sure I understand the picture. If K is the other knot, then what's V?
If K is the knot, then what is right, so I think maybe if you even get one, there to be about, four is like these four like 3 times I. Okay, great. Great. So this manifold V, it depends on whether it embeds into S4. So for us, when we're applying this theorem, want to sort of do a proof by contradiction, so we're not actually going to be working with the manifold B explicitly. So we're going to take our knot and build them into two-handle bodies that will extend over B if it exists, but if we get an inequality that's violated by the B2 and signature of our spin two-handle body, then we'll know that the manifold B doesn't exist. I guess that we don't actually need to work with the manifold B explicitly when we're doing our now the proof idea here is gotten by looking at maps on the H upper one. So if you look at H upper one of B with F2 coefficient, that maps to H upper one of boundary of B, which maps to H upper one of not complement, which is generated by the meridian of knot. So the idea is to show that this map is an isomorphism. The composition of these maps is an isomorphism. So you can study each of these maps individually with the Myers-Briggs sequence for F4 and also the boundary of B. Boundary of B is a knot complement union gluing in surface times F1. And then you can see that this map is an isomorphism, which tells you that there are two spin structures on the knot complement, and both of them will extend over B. So there are two spin structures on the knot complement. One is called F0, that's the canonical one inheriting this unique structure, spin structure from F3. And then there's the other one, F1, and they are distinguished by the characteristics, the characteristic length of a structure F on the boundary of B. Okay. That tells us whether spin structure F extends over a one frame two handle attached to the meridian of the knot K. This tells us which spin structure we're looking at if we restrict the knot complement. So if you look at a spin structure on the boundary of B, its characteristic length can be in K if only if it equals this non-canonical spin structure is not constant. And the characteristic length doesn't contain K because only if it agrees with its canonical spin structure on the non-constant. So to construct our spin F with F union being spin and your RNS boundary that is the same as the boundary cannot take. The first step is we'll take our Kirby diagram with that single two handle attached along K and the UGT1 handle, and we'll replace all the one handles with 0.2 handles. This operation preserves the boundary. So this is exactly the picture over here. And the characteristic length, let's use one containing K, but we don't know exactly which one. And in fact, it depends on the R covariance of not K. So it's K union some of those unknowns that you see in this Kirby diagram. And then the next step would be to alter the four manifold by without changing the boundary by a sequence of flow up, flow down, and handle flags until the empty vector is point. Is achieved. So in other words, we're going to alter the four manifold with these Kirby loops that don't change the boundary of the knot. We're changing the characteristic plane, so we're changing or we're not changing, right? So we're keeping track of the characteristic length at each step and keeping track of the Betti number, second Betti number in the signature, and in the end we'll arrive at a spin channel bottom that will have boundary that you can glue onto the beat, and a spin structure in the boundary will extend over B for one of the choices of characteristic length. And the inequality that we write down sometimes doesn't depend on the number of other components that you see here. So I actually think I'm out of time, but maybe the last step I'll just finish up. So our characteristic length is going to be K union C pairs of unknown union F single unknown. And after doing a blow up along each of the unknowns that you see, that doesn't change the characteristic length, but it changes the framing from the unknowns to +1. Then you can blow down all of the +1 unknowns that you see, and you would arrive at a new characteristic length for this new diagram, which looks like K connects a bunch of trefoils, C copies of the trefoil, and the framing on the characteristic length, instead of being 0 frames, now it's well, still 0 frames and C. And B2 and signature haven't changed. It's 1 B. So figure 0. And then finally, you can do take a diagram for the trefoil, which has three. You can grab 3 strands in a diagram for the trefoil and do a blow up to turn it into a diagram for T13 or an unknown. Each of these moves will affect the framing by a -9, and there's 3 of them. So we're doing C blow up, grabbing the 3 strands of the trefoil. These are -1 frame blow up. So we'll change the framing by -9 each time. So that's -9C on the characteristic. And now B2, for this 4 manifold, I haven't drawn the rest of the Kirby diagram. I've only drawn the diagram for the characteristic length. It's now 1 plus 2G plus C. Signature is now -C. So this is our framework for starting with any knot. You can take a characteristic length of this form, and you can use these blow ups and blow downs to get the characteristic length to just be your knot together with this framing and the B2 signature. And if you, depending on the knot, you have to do another sequence of blow ups and blow downs and handle slides to get to an empty characteristic length, which will produce for you a spin to handle body, to one of the choices of C and F will give you something that extends over B. And for a lot of our examples, the choice of C doesn't matter. You would get the same inequality either way, which is solved for the satellite knot example that I wrote down. So I'll just stop there, and I'm happy to take any questions. Thank you.